Welcome to this introduction to multivariable calculus. In single variable calculus, we study functions of one variable like f of x. In multivariable calculus, we study functions with two or more inputs, such as f of x and y, g of x, y, and z, or generally h of x1, x2, and so on up to xn. Today, we'll focus on functions of two variables, but the concepts we'll cover extend to functions with any number of variables. Let's start with the definition of a function of two variables. A function of two variables assigns to each pair of x, y in its domain a single real number, which we denote as f of x, y. Just like with functions of one variable, we have the concepts of domain and range. The domain is the set of all allowed x, y pairs, and the range is the set of all possible output values. Let's look at a simple example. F of x, y equals x squared plus y squared. The domain of this function includes all real x, y pairs, since we can square any real number. The range consists of all non-negative real numbers, since the sum of two squares can't be negative. Let's visualize this function. The function f of x, y equals x squared plus y squared, represents a three-dimensional surface called a paraboloid. The x and y values form the horizontal plane, and for each point x, y, the height of the surface above that point represents the value of the function. Notice how the function is 0 at the origin and increases as we move away from the origin in any direction. This makes sense because x squared plus y squared is always non-negative and grows larger as x or y increases in magnitude. Now, let's move on to limits of functions of two variables. The concept of a limit in two variables is similar to that in one variable, but now we're approaching a point in the plane rather than a single value on a line. We say that the limit of f of x, y is the point x, y approaches the point ab equals L if, for every positive epsilon, there exists a positive delta, such that whenever the distance from x, y to ab is less than delta but not 0, then the absolute value of f of x, y minus L is less than epsilon. The distance between points in the plane is given by the familiar distance formula, the square root of the sum of the squares of the differences in coordinates. Intuitively, this means that as x, y gets closer to ab, the value of f of x, y gets closer to L. Let's work through an example of finding a limit. Consider the function f of x, y equals 2x squared, y divided by x squared plus y squared, and we want to find the limit as x, y approaches the origin. Step 1. Let's make a guess for the limit. Looking at the function, we see that as x and y get close to 0, both the numerator and denominator approach 0. This is an indeterminate form, so we need to investigate further. Step 2. Let's check the limit along different paths. First, let's check along the x-axis, where y equals 0. Substituting y equals 0 into our function, we get 2x squared times 0, divided by x squared plus 0, which is 0. Next, let's check along the y-axis, where x equals 0. Substituting x equals 0, we get 2 times 0 squared times y divided by 0 squared plus y squared, which is also 0. Finally, let's check along the line y equals mx, where m is some constant. Substituting y equals mx, we get 2x squared times mx divided by x squared plus m squared x squared. Simplifying, we get 2mx cubed divided by x squared times 1 plus m squared, which equals 2mx divided by 1 plus m squared. As x approaches 0, this expression approaches 0 for any value of m. Since we get the same limit, 0, along all paths, we have strong evidence that the limit is 0. Let's formalize our finding with an epsilon delta proof. We want to show that for any epsilon greater than 0, we can find a delta such that if the distance from x, y to the origin is less than delta but not 0, then the absolute value of our function minus 0 is less than epsilon. First, let's manipulate the expression. The absolute value of 2x squared y divided by x squared plus y squared is less than or equal to 2 times the absolute value of y times x squared divided by x squared plus y squared. Now, x squared divided by x squared plus y squared is always less than or equal to 1, so our expression is less than or equal to 2 times the absolute value of y. If the distance from x, y to the origin is less than delta, then the absolute value of y is also less than delta. So if we choose delta to be epsilon divided by 2, then 2 times the absolute value of y is less than epsilon, which completes our proof. Thus, the limit of the function as x, y approaches the origin is indeed 0. Now, let's discuss continuity for functions of two variables. A function f of x. Y is continuous at the point a, b if the limit of f of x, y as x, y approaches b equals f of a b. In practice, most nice functions such as polynomials, rational functions where the denominator is not 0, exponentials and trigonometric functions are continuous on their domains. Let's look at an example of a continuous function. G of x, y equals x cubed plus 2x, y minus the sine of y. This function is continuous everywhere because polynomials and sine are continuous everywhere. Now let's examine a function that's not continuous at the origin. F of x, y equals x squared minus y squared divided by x squared plus y squared for x, y not equal to the origin, and f of 0, 0 equals 0. To check continuity at the origin, we need to see if the limit as x, y approaches the origin exists, and equals f of 0, 0, which is 0. Let's check the limit along the line y equals mx. Substituting, we get x squared minus m squared x squared divided by x squared plus m squared x squared, which simplifies to 1 minus m squared divided by 1 plus m squared. This value depends on m, so we get different limits along different paths. Therefore, the limit does not exist, and the function is not continuous at the origin. Let's look at one more example of a limit that fails to exist. Consider the function h of x. Y equals xy divided by x squared plus y squared. For x, y not equal to the origin. Along the line y equals x, we have h of x equals x squared divided by 2x squared, which equals 1/2. But along the line y equals negative x, we have h of x equals negative x squared divided by 2x squared, which equals negative 1/2. Since we get different values along different paths, the limit as x, y approaches the origin does not exist. Let's summarize the key takeaways from today's lesson. First, the definition of a limit for functions of two variables uses distances in the plane rather than just inequalities as in single variable calculus. Second, we can use the path test to check if a limit exists. If we get different values along different paths, the limit does not exist. Third, continuity means that the limit at a point equals the function's value at that point, just like in single variable calculus. Fourth, typical continuous functions include polynomials, exponentials, and trigonometric functions on their domains. And fifth, we should watch for indeterminate forms like 0 over 0, and check different paths to determine if a limit exists. I hope this video has helped you understand the basics of functions of several variables, limits, and continuity. Keep practicing with more examples to build your intuition for multivariable calculus.